Let's now talk about nuclear equations. In order to talk about nuclear equations, we first have to go over some of the various nuclear particles, some of which you've seen before and some of which you haven't seen before. You have seen the alpha particle, which is at the top of this table. The alpha particle is also seen as a helium nucleus. It has 4 nucleons, 2 of which are protons. It's a high energy nuclei that consists, as it says, of 2 protons and 2 neutrons. A beta particle is essentially a high energy electron. A positron is a electron-sized particle, but has a positive charge. It has the same mass as an electron, but has a positive charge. The positron you have not heard of before, and only occurs in certain situations with nuclear reactions. It does not occur in other situations. A proton is the same as a hydrogen nucleus, or it can be seen as a proton, a positively charged proton. It has the mass of a proton and a positive charge. A neutron, you're well aware of. It has almost the same mass as a proton, but has no charge. And then gamma rays are electromagnetic radiation. They are not particles. So the sum of the mass of the numbers of reactants must equal the sum of the mass of the numbers of the products. So this is the first principle when you write a nuclear reaction. You have to make sure you balance the mass numbers across the reactants has to equal the products. The sum of the charges of the reactants has to equal the sum of the charges of the products. And the atomic numbers determine what the element is. The atomic number that whatever an unknown has is what determines the identity of that element. So here are some examples of how to balance nuclear reactions. First, you conserve the mass number, A. On the left side of this equation, you have uranium-235 and a neutron, so the total mass number is 136. On the other side, you have cesium-138, rubidium-96, and 2 neutrons, so you have 138 plus 96 plus 2 times 1, and if you add all that together, you get 236 on each side. Secondly, you have to conserve atomic number or nuclear charge. With the same, now you're looking at the bottom subscript numbers. 92 plus 0 equals 55 plus 37 plus 2 times 0. And the biggest pitfall is to remember that an electron's subscript number is -1. And so you have to make sure you don't count it as a positive one. So let's look at some examples of how you would balance these various equations. So first of all, let's take a look at this top one. You have plutonium 242 94 breaks down to form an alpha particle, which is a helium nucleus, plus something. So 94 has to equal 2 plus something. So it has to be 92. So the subscript here is 92, and if you look that up on your periodic table, you'll find out what that is. Also, 242 has to equal 4 plus something. You subtract 4 from 232 and you get 238. So this is 238. And 92, if you look it up in the periodic table, is uranium. So plutonium 94 242 breaks down to form an alpha particle plus uranium 238 92. Let's take a look at this one right here. Something breaks down to form sulfur 32 16 plus a beta particle. So 16 minus 1 has to equal something, and that's going to be 15. So in here is going to be a 15. So the atomic number here is 15, and if you look on the periodic table, you'll see that that's phosphorus. 0 plus 32 is equal to whatever's over here, and that's going to have to equal 32. So it's phosphorus 32 breaks down to form sulfur 32 plus a beta particle. This is called alpha decay. When something breaks down to form an alpha particle, this is called alpha decay. And this is called beta decay, when something breaks down to form a beta particle. So let's take a look at this one right here. You have californium, 252.98 plus something forms 3 neutrons plus lawrencium 259.103. So first of all, 3 times 1 is 3 plus 259 has to equal something, 252. Well, that something, this plus this is 262, so this is going to have to be 10. And then down here you have 103 plus 0 times 3 has to equal 98. Well, if you look at that, that's going to be 5. So it's going to be 5, and on the periodic table, 5 is 7's carbon. I can't remember. Oh, boron. Boron is 5. Now this one here is iron 55, 26, plus something equals manganese 55, 25. So 55 plus something has to equal 55. Well, that's going to be 0. 26 plus something has to equal 25. Well, that's a minus 1, so that's going to be a beta particle. The last one here is oxygen 15 breaks down to form something plus a beta particle. So it's a positron. I misread that. Got to be careful there. So it's a positron. And so you've got something plus 1 equals 8. And on the top side, you've got 15 equals something plus 0. So that's going to be 15 there. And this has to be 7. So this is 7, 15. And that's nitrogen. So oxygen breaks down to give off a positron and leaves us with nitrogen 15. And so that's how you balance these nuclear reactions, is you make sure that the atomic mass balances on both sides and the atomic number balances on both sides. So let's look at radioactive decay. Here's an example of an alpha decay. Any radioactive decay is a spontaneous change in an unstable nuclei. Uranium-238 is unstable, and it spontaneously breaks down to produce an alpha particle, and thorium-234. The parent nuclide is the unstable reactant, and the daughter nuclei is what results from the decay. So a nucleus of uranium, which is the parent, undergoes alpha decay because it produces an alpha particle to form thorium-234, which is the daughter. The alpha particle removes 2 protons, which are green in this picture, and 2 neutrons. Alpha particles, which are attracted to a negative plate because they're made up of 2 protons and 2 neutrons, can be deflected by a small amount of negative charge. So alpha particles, which are attracted to a negative plate and deflected by a relatively small amount, must be positively charged and relatively massive because they're only changed a little bit. Beta particles, on the other hand, which are attracted by this positive plate, are deflected in a greater degree because they're negatively charged but relatively light. Gamma rays, which are electromagnetic radiation, are unaffected by a charged field. So this shows that this experiment would show that alpha particles are positively charged and heavy, beta particles are negatively charged and lighter, and gamma rays are neither positive nor negatively charged. This table shows the various kinds of decay, which I also reviewed for you in the previous problems we were doing. Alpha decay, we've already gone over, is when an alpha particle is released. The A has to decrease by 4, that is, the atomic mass decreases by 4 from parent to daughter, and the atomic number decreases by 2 from parent to daughter. Beta decay is when a beta particle is released. The atomic mass is unchanged, and the atomic number increases by 1. Gamma decay changes neither the atomic mass or the atomic number. Positron emission, which is we showed as one of our examples, I believe it was the one with nitrogen, the atomic mass is unchanged and the atomic number decreases by 1. And then another we did not talk about is called electron capture, which is when an electron is added to the parent and it produces a daughter that has an unchanged atomic mass but an atomic number that's decreased by 1. A PET scanner, which is shown on the left here, uses radiation to provide an image of how part of the body functions. The most common is called an F18 image because F18, fluorine, is formed. You inject a glucose molecule that contains oxygen 18, O, and 8, and it's called a PET, or positron emission scanner, because a proton is added to form the fluorine. And the scan releases energy which can be detected by a detector. The advantage to this scan is it doesn't just show anatomic, but it also shows functional, because it shows those areas that are actively taking up glucose and metabolizing versus those that do not. B here represents a healthy brain, which takes up a lot of glucose when it's working, and C represents an Alzheimer's brain, which because of its dementia has far less metabolic activity. This shows a series of decay reactions. These can be called sometimes a chain reaction if this continues without any outside help. And what you see is you start with uranium and you go through a series of steps until you reach the uranium's up here on the right, upper right corner. At the end, you reach lead-206, which is a stable element. And through all this, you have several unstable intermediaries or daughters. So this is called a radioactive decay series. This is a naturally occurring radioactive isotopes of the heaviest elements fall in chains of successive disintegration or decays. And this continues in this chain until you reach a stable element. So uranium-238 undergoes decay in a series with 14 separate steps until it produces the stable lead-206. This series actually has 8 alpha decays and 6 beta decays.